Hello, ladies and gentlemen. This is going to be your notes on solutions and solubility. So to start out, I just want to define what a solution is really quickly. And in terms of this class, we are going to define a solution as a solid substance dissolving into a liquid substance. So those two things together, that solid and that liquid together, are going to be a solution. A couple of terms you should be aware of, though. If you see the term solute, that means solid. And then if you see the term solvent, that means liquid. And again, if you put a solid and a liquid together, you get a solution. All right, and again, you've heard of solutions before. You know what solutions are. We used a couple of them on Friday. So to put salt water in the lens of solid plus liquid, when we make salt water, which is our solution, we have our solid substance salt plus our liquid substance water, and our solution is salt water. So that's a pretty easy concept to understand. And there's a little graphic down here below that kind of shows you what that looks like on a particulate level. Another term that I really need you to be aware of, though, is the term polar. All right, so let's write down the word polar. If a molecule is going to be defined as polar, it has a more positive end, or pole, and a more negative end, or pole. So let's write down that definition. And then one of the most well-known examples of a polar molecule that I'd like to show you is water. So if you remember from first semester, we drew Lewis dot structures, and then we figured out what shape they were. And so if you're going to draw water in the proper shape, this is what it looks like. All right, we have H2O, two H's, one O, and that molecular shape overall was bent. All right. Now, the shape is actually really, really important for determining polarity because the shape quite often produces the different ends of the molecule. So in this case, oxygen up here is going to represent the more negative end of the water molecule. And the reason for that is because oxygen as an atom is really electronegative, which means that it's pulling on electrons really, really hard. So you can think of oxygen as kind of an electron hog. It likes to keep electrons with itself, and electrons are negatively charged. So if oxygen's hogging all the electrons, oxygen's going to be pretty negative overall in that molecule. And hydrogen, on the other hand, not really an electron hog, not very electronegative. So overall, those hydrogens are just a little bit more positively charged overall. So this end of the water molecule is its negative pole, and that end of the water molecule is its positive pole. All right? Now we're going to contrast that really quickly with a non-polar molecule. So I'm just going to label this one polar really quickly. And then over on this side, we're going to have a non-polar. I'm just going to draw it for you. If we're thinking about the molecule CH4 or carbon tetrahydride, let's see the difference between this one and water. There's no electron pairs anywhere to produce that overall negative charge. Carbon and hydrogen actually have pretty similar electronegativity values. So if we were to try and assign poles to it, it would kind of be impossible, right? Because hydrogen is pretty positive all over the place, right? So you don't see any difference across that molecule. All of the ends of this molecule are positive. And you could define that carbon in the center as just a hair more negative, but carbon's hidden in the center. And so no matter where you're at on the outside of this molecule, it's positive all over the place. So it doesn't really have any clear poles. So we would call the CH4 molecule nonpolar, whereas water, on the other hand, is polar because it has those opposite poles. Okay? Now, when we're asking ourselves, can one substance dissolve in another substance? We are asking ourselves if that substance is soluble in that other substance, right? So solubility is, can it dissolve? All right, and 90% of the time in this class, we're going to be asking ourselves if a substance can dissolve in water. Not every single time, but most of the time. And depending on the type of molecules we're looking at, we are going to be using different rules. So if you're looking at a covalent substance, for example, we're going to use the rule like dissolves like. Basically, polar substances can dissolve in other polar substances, and nonpolar substances can dissolve in other nonpolar substances. And again, that is the rule that we're using when we're talking about a covalent substance. And to remind you what a covalent substance is, it's composed of nonmetals. All right? Now, some examples of covalent substances that can dissolve in water, because water is polar. We have sugar, sugar is a polar covalent molecule, so sugar can dissolve in water. Also, alcohol in water. Alcohol is a polar molecule. Water is a polar molecule, therefore alcohol can dissolve in water. But if you want an example of something that could not dissolve in water, oil is a beautiful example. Oils are nonpolar, kind of like the CH4 over there. So oil cannot dissolve in water because since oil is nonpolar, it will not dissolve in a polar substance like water. All right? However, if you're talking about a nonpolar substance like oil, trying to dissolve in another nonpolar substance like wax, or vice versa, wax can dissolve in oil, oils can dissolve in wax, those are fine because both of those substances are non-polar. All right? If, however, you are talking about an ionic substance, right? And if an ionic substance can dissolve in water, we're going to use the ionic solubility rules, which is this giant table down here. All right? And if you forgot what an ionic substance is, that's something that's made up of a metal and a nonmetal. All right, so can this thing dissolve in water? We have to look at our table, okay? So the table just has a few rules to tell you what types of ions are likely to dissolve well in water, because not every single ionic substance will dissolve in water. Some will and some won't. And the reason for that is it has to do with the strength of those ions' attraction for each other and the strength of their attraction for water, okay? So here, I'm going to draw a little line about halfway down this table so it's super, super obvious. These ions up top, all of these guys, are mostly soluble. They are totally fine to dissolve in water. So we're going to label those soluble. Right? So if you see sodium or potassium or lithium or ammonium or nitrate or acetate or chlorine, bromine, iodine, fluorine, sulfate, most of those ions are going to be soluble most of the time. The descriptions over on the right-hand side list some exceptions, right? So let's talk about one of the exceptions here. So the chlorine ion, mostly soluble in water. So if you see a molecule that has chlorine in it, that molecule is probably soluble. But if, however, that chlorine happens to be paired with silver, like in silver chloride, Silver chloride is not soluble because silver is an exception to chlorine's solubility rule. All right? Down here on the bottom, we have some examples of ions that are generally insoluble, meaning they usually cannot dissolve in water. So carbonates, phosphates, hydroxides, and sulfides generally cannot. And the exceptions over here are to say that, hey, carbonate is usually not soluble in water, but if it's paired with something in group 1 on the periodic table, like say sodium or potassium or something like that, because all of those are in group 1, then that molecule would in fact be soluble. All right, so I know that sounds a little confusing, but let's look at some examples for how you're going to use this table. All right, we have a practice over here. Now, our first molecule, our first ionic molecule that we are going to ask ourselves about is aluminum chloride. All right, so what we're going to do is we're going to look at our two pieces of this compound, aluminum and chlorine, and we're going to look for both of those on the solubility list. So I don't see aluminum anywhere on this little list of ions, but I do see chlorine. And chlorine is in the soluble section, right? So just as a quick glance at this, I'm thinking, okay, aluminum chloride, I should say, is probably soluble. But let's check the exceptions. I don't see aluminum as an exception listed with chlorine. So hey, guess what? This thing is soluble. All right, let's try another one. We have barium sulfate. Once again, we look for barium, we look for sulfate. The first one I'm seeing is sulfate right here. Sulfates are listed as soluble. All right, so first glance, this thing might be soluble. Let's look at the exceptions and check if barium is an exception. Sulfates are soluble except when paired with barium. And so since sulfate is paired with barium over here, that's going to be an insoluble. All right. Next one. Silver iodide. Once again, we look for silver, we look for iodine on here. First one I see is iodine. Iodides are generally soluble, except when paired with silver. So this thing is also going to be insoluble. All right, last one. We have silver nitrate. I look for silver, I look for nitrate on there. The first one I see is nitrate. Nitrates and acetates are soluble. I do not see any listed exceptions to that rule, so this is going to be a soluble ionic compound. All right, that's how you use the solubility rule table. Now, just popping back over to this left-hand side right now that we've looked at the solubility rules and we've looked at some rules for why things cannot dissolve, I want to just talk about what happens when ionic substances dissolve in water. All right, so I'm going to draw a quick little line here. And I'm going to draw a water molecule. Once again, we've already talked about how water is a polar molecule. So I'm just going to draw it real quick and add those little partial negative and partial positive ends. And then I'm going to draw sodium chloride. All right. Now, we know that sodium chloride is an ionic compound composed of two oppositely charged ions. Sodium is your positive ion, chlorine is your negative ion. And if you're not sure how I figured that out, I looked at the periodic table because sodium has a positive 1 charge, chlorine has a negative 1 charge. So when we drop this solid sodium chloride into water, what happens is there's some attraction here, right? The negative end of water is going to be attracted to that sodium, and the positive end of water is going to be attracted to that chlorine, right? Because we know that oppositely charged ions attract one another. And because of that attraction is so strong that it's actually going to break this bond. All right, so literally that's how dissolution works. Water is strong enough to break the ionic bond between sodium and chlorine. And if I were to draw that same substance, but this time dissolved in water, I'm going to redraw my water molecule with its more negative end and its more positive end, right? And then what I have to do is I have to move my ions to what they were attracted to. Okay, so my positive sodium is going to hang out with the negative end of water, because again, it's attracted to it. And my chlorine ion is going to hang out with the more positive end of water because it's attracted to it. So this would be dissolved. And we can see the clear difference, right? We can see that whereas it was bonded up here, now it's no longer bonded, and we just have some ions floating around next to those water molecules, right? And we can totally represent more waters if we wanted to, because if you're dissolving salt in water, there'd be a bunch of waters around, right? There'd be some waters here. There might be some waters there, right? And those water molecules are going to kind of orient themselves around the ions that are dissolved into them. All those oxygens are going to organize themselves around the sodium. All the hydrogens are going to organize themselves around the chlorine because of that attraction. Okay. Okay, so now we've talked about how ionic substances can dissolve. We've talked about what kind of substances can dissolve in water. Now we want to talk about degrees of saturation, which is a fancy way of saying how much solid have I attempted to dissolve so far. So let's just say I have a beaker, right? And that beaker has, I don't know, whatever. Let's say it has 100 grams of water in it, right? I cannot keep dumping salt in there and expect infinite salt to dissolve in that water. At a certain point, I am going to oversaturate the water in that beaker with salt, and that salt will stop dissolving. So that's kind of what I'm talking about when I say degrees of saturation. If I have an unsaturated solution, that means that I have not yet hit that water's capacity, right? I can still dissolve some more salt in that water. And that's why over here in the little graphic, you're seeing that, hey, there's this little test tube. It has water in it. I'm not seeing any solid at the bottom because I can still dissolve more salt or sugar or whatever it is. However, again, once I keep dumping salt in there, eventually I'm going to hit the saturation point of that amount of water that I have. And no more salt is going to dissolve. So right at that point, right when the salt stops dissolving, that is a saturated solution. But let's say I keep trying to dissolve more salt. I keep dumping more salt in there. At a certain point, once I pass my saturation point, I'm going to super saturate it. So if you've ever tried to dump salt and dump salt and dump salt into the same amount of water, eventually it just sits at the bottom and there's a bunch of solid left over and it's no longer dissolving. That is a super saturated solution. So we have our unsaturated where I can still put more salt in there. I have my saturated solution where I've just hit the water's capacity for salt. And then I have a super saturated solution where I've gotten a little dumping salt happy and I've way exceeded the capacity of that water to dissolve the salt. All right. And that is what forms solubility curves. Now, solubility curves is a good portion of what the practice you're going to start working on today is about. And what a solubility curve is just a graph, and it compares a bunch of different ionic substances and their ability to dissolve in water at various temperatures. Because one of the ways you can increase water's ability to dissolve stuff into it is by heating it up, right? So let's say at 0 degrees, I can dissolve 10 grams of salt in this water, but at 100 degrees, I can dissolve 30 grams of salt in this water. Again, messing with the concentrations, messing with the amount of salt, messing with the temperature, we can create this graph that just tells us how much salt will dissolve in water at any given time. Okay? So, to read the graph is actually pretty easy, but we have to understand what the lines mean first. So let's look at this line up in the corner, right? This Ki line. This line for Ki, this is the saturation line. Right? So that saturation line is the maximum amount that can dissolve at any given temperature. Right? So according to this line, on this graph, at 0 degrees Celsius, I can dissolve a maximum of just under 130 grams of potassium iodide in 100 grams of water. So going back to my beaker example, this graph has standardized for 100 grams of water. So we have that much water, I can dissolve 130 grams of potassium iodide in it. But if I increase that temperature to 10 degrees, then my maximum amount of Ki goes up and I can dissolve, let's say, 137 grams of potassium iodide in that same 100 grams of water. If I increase the temperature a little bit more to 20 degrees, then suddenly I can dissolve up to roughly 145 grams of potassium iodide at 20 degrees Celsius, and so on and so forth. All right? So let's look at our practice questions. It says, what concentration of KCl will dissolve at 50 degrees Celsius? Okay, so I find the KCl line, which I'm just going to draw on that so it's easier to see. Okay, and it asks me what can dissolve at 50 degrees, right? So I go to my 50 degrees and I find that line. I go, okay, well that is about 40. It's almost 40 exactly. So we're going to say, okay, at 50 degrees, 40 grams of KCl will dissolve at that temperature. Cool, amazing. Now let's go over to question 2. It says, what temperature is needed to dissolve 60 grams of KNO3 or potassium nitrate? So we find the potassium nitrate line. Again, I'm going to draw it so that it's a little bit easier to see. All right, and it says, okay, at 60 grams is what I'm trying to dissolve. So I go to 60 grams. I go, okay, well, what temperature do I need to dissolve that much? What temperature do I hit the line? And that is going to be at 40 degrees. All right, cool. Last question. This one's a little bit more complicated, still not terrible. If you put 30 grams of KNO3 in 100 grams of water at 50 degrees, how much more could you dissolve? Okay, so there's a little bit more information here. I know that I've put 30 grams in already, right? I've put in 30. I know that I'm at 50 degrees, and I know that I'm still dealing with KNO3. So let's find my line at 50 degrees, and it says, maximum of 80. So this question is asking, well, I've put in 30. If my maximum is 80 grams, then how much more can I put in? Okay, well, I do 80 minus 30, and I get 50. Right, so basically it's just saying, okay, if you've put in 30 already, how much more until you hit that line? Because if we remember, our line is our maximum amount. So all we had to do is simple subtraction. Okay. This last bit is particulate level diagram. So this bit is maybe the most complex, and it's not complex because it's impossible. It just is going to combine a few skills for you. Okay? So our particulate level diagram says diagrams that show how molecules act at the molecular level. You can use them to show the phase, solid, liquid, gas, or aqueous of molecules. Now, a couple of you asked me, what does S, L, G, and AQ mean? Because you saw those things on our last test review, and you were like, what are those letters? And I just said, hey, it's a phase symbol. Don't worry about it right now. Now we're going to start worrying about it. So solid, S, L is liquid, G is gas, and then AQ is aqueous. Now, aqueous, I mentioned already on the other side, I said it a couple of times, but aqueous quite literally means dissolved in water. Right? That's what the word aqueous means. So there's a couple of important pieces of information here that you're going to have to worry about. One, if I'm assigning something solid phase, that thing is going to be insoluble in water. However, if I assign something the aqueous phase, that means that it's soluble in water. And I know that specifically because if something can dissolve in water, it has to be soluble, right? So we're just going to write that down to remind ourselves. Now, if I want to draw a particulate level diagram of this particular chemical equation, the first thing I have to do is write it out chemically. So we're going to do that real quick. We have potassium carbonate, right? We have potassium and we have carbonate. To write that properly, you have to swap and drop it because it is an ionic compound. So we have K2CO3. All right. Next one, silver 1 chloride. We have silver, and I am told that it's silver 1, so that's going to be a +1 charge. Chlorine is a -1 on the periodic table. Again, we're going to swap and drop those, but they neutralize each other. So we have AgCl. We have potassium chloride. Potassium is a +1 charge on the periodic table. Chlorine's still a -1. Again, we swap and drop it again, but they are a +1 and a -1, so they neutralize each other. And then lastly, we have our silver 1 carbonate. Our silver is still silver 1 with a +1 charge. Carbonate still has a -2 charge, so we swap and drop those, and we have AgCO3. All right, so we have our unbalanced skeleton equation. First thing I'm going to do is balance it, just like we're used to doing. Now, I am going to assign my phase symbols. So I'm going to do that in a different color so it's super obvious. Phase symbols, S, L, G, and AQ, again, solid, gas, liquid, aqueous, they go in these little parentheses to the right of your chemical. And all it's going to do is it's going to tell you what is the phase of that thing. Is it a solid thing? Is it a gas? Is it a liquid? Or is it dissolved in water? For us, the only two phase symbols that we are going to care about during solutions are solid and aqueous, because again, we're dealing with solutions, which are solids dissolved in water, or not dissolved, depending on what kind of substance they are. So we want to decide whether each of these chemicals is solid, insoluble in water, or aqueous, dissolved in water. And to do that correctly, we got to look at our solubility rules. So I'm going to let you flip over your own notes rather than me flipping back and forth. But we know, based on our solubility rules, that carbonates are generally insoluble. So that's what carbonate is. But an exception to carbonate's insolubility is anything that is in group 1 on the periodic table. So since carbonate in this case is bonded to potassium, which is in group 1, that means that this thing can dissolve in water. It is soluble. So we would define it as aqueous, which I'm just going to write that below. That means soluble. All right. Next, we have silver chloride. Chlorine is generally soluble, but an exception to its solubility is silver. So we're going to define that as a solid or an insoluble substance. All right. We have potassium chloride. Again, chloride's generally soluble. Potassium is not an exception to that rule, so we're going to define it as aqueous or soluble. And then last but not least, we have silver carbonate. Carbonates are generally insoluble. Silver is not an exception to that rule, so we're going to define it as solid or insoluble. All right, why did I do that? I did that specifically so I could figure out how to draw those things at the molecular level. All right, so we have our 3 beakers here. So let's imagine for a second that we are performing this reaction. That means that I have separated potassium carbonate and silver chloride, and I am going to mix them together to see what happens. All right, so I'm going to label my reactant beakers. This reactant beaker is going to be K2CO3. This reactant beaker is going to be my AgCl. And then if I mix them together, that means that the one after the arrow is going to be my product beaker, but both products are going to be in there because I mixed them together. So KCl and AgCO3. All right, so that's just telling you which chemicals to put in what beaker, because again, I'm mixing them together. All right, and the way I'm going to do this is I'm going to use my phase symbols to tell me what to do, right? So this one, the phase symbol for potassium carbonate, which is going in this first beaker, is aqueous, and we know that means soluble. Since potassium carbonate is soluble, that means that I'm going to draw it in solution. I'm going to split it up, right? So I'm going to put my water in my beaker because this is my solution, and I'm going to put a water molecule in there. My cool little bent water. I'm going to keep it kind of small to give myself enough room to do other things. And since I know that this potassium carbonate was soluble, I'm going to split it up, much like I split up sodium chloride on the front, right? If I split this up, this K2CO3, I'm going to split it up right there. And then it's going to split up into 2 potassium ions and a carbonate ion, right? Just like before swap and drop. Since I know that water is polar, that means that my 2 potassium ions are going to hang out with the more negative end of water. And since I know that hydrogen is my more positive end of water, that means my carbonate ion is going to hang out with it because I know that negative and positive charges are attracted to one another. So this is literally what's going on in that solution. I have some water molecules, I have some potassium ions floating in there, and I have some carbonate ions floating in there. So let's take a look at my second reactant beaker, my silver chloride. Okay. In this one, I notice that my phase symbol is solid, right? And insoluble. So I'm not going to draw it split up because it's a solid substance. Why would I do that? Instead, I'm just going to draw my substance at the bottom as a solid. It's like a powder or a salt. Okay, now again, let's picture it for a second. I have two beakers, one with a solution in it, one with a solid powder. And then I'm going to mix those two things together into one beaker and see what happens. And those two things are going to react with one another and they're going to produce products. Okay, so both of my products are going to have to go in this third beaker. So once again, I still have some water in there, so I'm going to draw it real quick. And I have two products to pay attention to. One of them is soluble, so I'm going to split that one up. And one of them is insoluble, so I'm not going to split that one up. The insoluble one, I'm just going to put on the bottom, right? Because that one's just going to be a solid. It's going to sink to the bottom. But the aqueous one, the potassium chloride, that one I'm going to split up. I'm going to put my potassium ion and my chlorine ion next to the ends of water they're supposed to be with. My potassium ion is positive, so it's going to hang out with the more negative end of water here. And since the hydrogen end of water is more positive, my negative chlorine ion is going to hang out with it. All right, so this is my particulate level diagram for what has happened in this reaction. I had my two reactant beakers and I mixed them together to see what happened during that reaction. Okay, if you have any questions, please ask me during class on Tuesday. I will see you all tomorrow.